Ladies and gentlemen, good morning. I'm Xingguo, a PhD student from University of Macau. Today, I'm so excited to present our work, Expeditious High-Concurrency MicroVM SnapStart in persistent memory with an augmented hypervisor. In this work, we introduce a system leveraging byte-addressable PM for cost-effective and highly concurrent SnapStart execution. Let's begin with SnapStart. SnapStart is an approach that leverages snapshot restore technique to bypass time-consuming cold start and accelerates function execution by reusing previously saved memory state. In non-SnapStart, we go through sandbox initialization, resource allocation, library and package loading, and function loading, and finally, function execution. With the SnapStart, we need only one snapshot restoration, and only one time snapshot restoration recovers all runtime states, allowing immediate function execution. Compared to non-SnapStart, SnapStart to reduce cold start delay from seconds to milliseconds. An Amazon research group introduced the MicroVM in Firecracker project at NISTI 2020. MicroVM is a lightweight VM tolerated for short-lived workloads. MicroVM serves ideal sandboxing solution for production SnapStart, such as Lambda SnapStart, because they provide lightweight KVM-based virtualization and VM-like security. More importantly, they enable rapid startup with minimal memory footprint, which is ideal for short-lived crowd applications. In crowd environments, cold start issues are common. There are three solutions. Number one, reducing booting time. Number two, reusing memory states. Number three, leveraging snapshots for fast restoration. And in this work, we call the third approach as SnapStart. As we all know, keeping instance always alive has low cold start delay, but occupies a lot of memory resources. Reducing booting time has upside effect. So SnapStart serves as a trade-off between cold start delay and memory resource occupation. It enables near-instant responsiveness to incoming requests while has a minimal memory footprint. And existing SnapStart has pros and cons. The advantage is rapid startup by memory mapping the snapshot file into guest memory. Since the guest memory is loaded on demanded, there's no upfront cost during initialization. However, the downside is slow execution due to frequent major page faults. When the guest accesses non-resident pages, triggering context switch, scheduling, and demovement overhead, leading to significant execution slowdowns. The state-of-the-art FaaSnap from USENIX 2022 aims to reduce major page faults by prefetching working site. It consists two phases. Number one, record a guest working site and save it to a compact file. Number two, during invocation, prefetch working site from disk. Prefetching the working site would reduce guest page faults, thus accelerate program execution. However, it cannot be suitable for high concurrency scenarios and other memory architectures like persistent memory. And we'll discuss the details later in the case study section. Our biggest motivation is that in snapshot scenarios, PM can replace the DRAM plus SSD tiered architecture to achieve high cost effectiveness and good performance. High cost effectiveness comes from PM's huge memory capacity with a low production price. And good performance comes from persistence and the faster recovery capability of the single-tiered persistent memory. Let's first look at SnapStart execution on the traditional hierarchy memory architecture. When a virtual machine accesses a memory page, if the snapshot page is already loaded into DRAM, it is immediately returned. Otherwise, a page fault is triggered, causing pause, context switch, and loading the snapshot memory page from disk into DRAM before resuming VM execution. Frequently triggering major page faults leads to expensive performance penalties. And the expensive overhead of page faults mainly comes from costly demovement because of the significant latency gap between DRAM and disk storage in modern computer memory hierarchies. So, we envision a hardware solution that supports memory operations and a low direct CPU access to minimize the gap. In 2019, Intel introduced the first commercial persistent memory. It has low latency, with read and write operations taking around 100 to 300 nanoseconds. Second, it supports bit addressability with a cache line granularity of 64 bytes. Third, it has large capacity, supporting up to 8 tag bits per machine. Last but not least, it's non-volatile. That means data stored in persistent memory remains even after a power outage. And our idea is PM's single-layered structure can help skip the tiered memory access and costly demovement in snapshot scenarios. Snapshot pages are persistently stored and directly accessible in persistent memory all the time, enabling efficient and stable VM access. Intel Optane persistent memory has 3 modes: memory mode, DEX mode, fail I/O mode. And the DEX mode facilitates maintaining persistence and bit addressability, aligning with our goals of doing unified memory management like DRAM. Such a commercial PM under DEX mode provides a viable platform to implement our idea. However, implementing this idea is not straightforward. The first challenge is how to establish effective mappings efficiently. Common mapping approaches include lazy loading, partition mapping, and fully mapping. Lazy loading has the fastest VM restoration time, but has the slowest function execution time, while full mapping has the opposite effect. Partition mapping lies in between, but requires deciding which portion to map ahead of time. Such adopting existing mapping schemes is insufficient to fully unlock the PM's performance for MicroVM SnapStart. The system for MicroVM SnapStart employs lazy loading in default, which enables fast VM restoration time, but still suffer from page faults, leading to significant performance slowdowns. And the second challenge is how to maximize the direct access benefits of persistent memory, ensuring we bypass cache media iteration. To accelerate the process of snapshot memory page access, while directly mounting snapshots on a DEX-enabled file system seems promising for supporting direct access. It can lead to expensive DEX faults. These errors occur due to memory semantic mismatch between the persistent memory file system and the virtual machine's memory semantics, preventing mutual awareness and seamless integration. The third challenge involves ephemeral workloads, especially for non-iterative single-access workloads with many ephemeral pages. They are accessed once and quickly discarded. Traditional caching techniques on multi-tiered memory architecture cannot efficiently handle ephemeral pages due to unnecessary copies for this page being cached into DRAM, leading to slower performance. And we also conduct a lot of case studies to validate our hypothesis. In our case study, we found page faults account for 40 to 60% of the VM's lifecycle time, both on PM or SSD, indicating page faults as a major bottleneck in SnapStart execution. In an ephemeral workload case study, we found minimal difference in SnapStart latency among various approaches. And third, we tested FaaSnap under concurrented workloads, comparing it to an ideal scenario where all snapshots are cached into DRAM. As we can say, as concurrency increases, FaaSnap's average execution time grew significantly, indicating FaaSnap's poor performance under high concurrency. First, we ran FaaSnap on persistent memory and SSD and found that the execution time on PM was slower than SSD in almost test workloads. That means FaaSnap does not work well on PM. The reason is FaaSnap cannot record the accessed working site on PM because the access are now cached. In ResNight 50 workload case study, DEX faults accounts for nearly 30% of SnapStart execution time, significantly impacting function efficiency. And this case studies reveal, number one, page fault overhead critically hinders SnapStart execution time. Number two, the DEX feature in PM can enhance memory access efficiency for certain ephemeral workloads. Number three, high concurrency significantly degrades FaaSnap's performance. Number four, FaaSnap's prefetching is incompatible with PM DEX feature. Number five, MicroVM memory snapshots on PM file system underutilize DEX capabilities. So our opportunity is directly management of PM, avoiding traditional file system may optimize SnapStart's use of PM's performance potential. In past, our goal is to reduce time spent on page faults and date moment for end-to-end SnapStart execution. And our high-level idea is to leverage PM direct access into MicroVM with complete address indexing. And our design includes two hypervisor embedded components, the persistent memory manager and the MicroVM manager. The workflow starts with initializing PM space and snapshotting all memory data to PM. Then the PM manager extracts the data by paging, establishes mappings, and maintains an active state. The MicroVM queries the hash table to obtain the required snapshot memory, and build complete address indexing and synchronizes mappings to KVM space. First, we propose adopting complete address indexing in our MicroVM manager to pre-fault page mapping. Unlike traditional lazy loading or partition mapping schemes, our design completely maps a memory snapshot to the VM memory. This approach avoids fragmented mapping and online mapping reconstruction and demoment, thus making it highly efficient. Furthermore, we perform lifetime management of address indexing from VM start to VM shutdown. The address range built for VM is unique to that VM during its lifetime, avoiding address conflicts. Crucially, we register the address indexing to KVM space, synchronizing and coordinating memory semantics. Moving on, our embedded PM manager is responsible for zero-copy on-demand paging. We observed the PM snapshots, the memory snapshot space on PM remains stable during SnapStart. The file system becomes redundant. Operations on PM file system for SnapStart incurred additional context switch and even expensive DEX faults due to memory semantic mismatch. By eliminating the file system layer like what we are seeing in the right line, our embedded PM manager enables the hypervisor to operate directly on user space memory. It cuts down unnecessary context switches and coordinates memory semantics. Seamlessly compatible with common memory instructions, our approach allows the hypervisor to enjoy the benefits of direct access to PM. Finally, we propose a hash table to bridge the VM manager and PM manager. Its primary function is to manage the states of memory snapshots, offering a match between VMs and snapshot memory and reserving pre-built indexing on PM for guest memory. For more information on PM, address management, programming interface, and other implementation details, please refer to our paper. And in our evaluation, we choose 4 other approaches for comparison and select non-workloads for performance measurement. For end-to-end SnapStart execution time, PaaS achieves up to 72 reduction compared to the vanilla, and 47 reduction compared to FaaSnap. And PaaS achieves similar performance to DRAM cached approach. PaaS significantly improve performance in ephemeral workloads. In released workload, PaaS outperforms the vanilla by over 6 times and FaaSnap by 4 times. For scalability, with 32 concurrent instances, PaaS outperforms the vanilla by 1.56 to 6.38 times, and FaaSnap by 1.38 to 4 times. As shown in the right top figure, PaaS outperforms FaaSnap by 1.6 times and by vanilla 3.5 times in an ephemeral workloads. For non-ephemeral workload, PaaS matches or slightly outperforms competitors. In conclusion, in PaaS, we propose pre-fault page mapping and zero-copy on-demand paging technologies for leveraging PM in SnapStart. PaaS achieves up to 72% better latency performance and 2.2 cost effectiveness compared to Firecracker. And thank you for your attention. I'm happy to answer any questions you may have.